Hi, everyone. I was delivering a talk just a few minutes ago in the other room, so I will give the stage for my colleague, Dr. Qassim, but I will give a couple of thoughts of our research group, Open UAE, in the University of Sharjah. So basically, we are leading a nice initiative on the country level with the TRA for leading the open source initiatives in the country. We know that open source is blooming and building governments out there in Europe and North America, but we don't have a unified efforts or combined efforts on the Middle East. So we hope that our research group will be leading something on the country, and we link the things that are done in the Arabic countries. Actually, there are great efforts, but unfortunately, we don't have an association or a group that can, or a community that can lead or combine all the perfect or the wonderful job that they are doing in the open source. Our research group directions are in the AI, blockchain, and IoT. So anything that we develop, we really put it on the open source in the GitHub for the benefit that could the community have. And the projects that we do have nice partners like Dubai Electronic Security Center, Ministry of Education, because we're trying to approach the youth so that we build the awareness about having the open source community and open developers who can be keen on the coding and programming and to contribute more in that sense. And we delivered actually a workshop last year to 700 high school teachers for the open source in order to have hands-on and to try to put the awareness to this youth generation. And this thing we started last year, and we hope that we continue with the Ministry of Education. We also have other partners like Emirates NBD, the TRA, that we are working on a different level of projects. One of them is for the blockchain, having the infrastructure of blockchain for managing IoT devices so that we can have cheap, fast, secure solution for managing the IoT devices for the government services. And we do have the IoT test bed. We are trying to have the automated one in our research group. That's both projects are funded and sponsored by Dubai Electronic Security Center. We also work in the inter-blockchain with the Emirates NBD, and we are trying to have different heterogeneous and other platforms to be connected and talk to each other, having the transaction between different platforms. And we do work with the AI in different also directions with the Ministry of the Interior, trying to capture all what is in the recent and the crime analysis, the intrusion detection, and the other directions. So basically, we hope that anybody, if you are interested to join us into these projects or even community level, we do have a group and WhatsApp that try to have ambassadors from all the universities on the country. So we have a point of contact with each university, a doctor and the Department of Computer Science or Engineering, or some directors of the IT center. We also have an ambassadors from the private and the public sectors, so that we can be as a closed community that can spread the awareness and can get them involved and engaged to the community. So nice meeting everyone here. I will give the floor to Dr. Qassim to have a hot topic for you, blind digital signatures.
Assalamu alaikum. I'm Dr. Qassim Nasir from College of Engineering, University of Sharjah. It's good to talk about the University of Sharjah for 1 minute, to tell you about it. We have about 14,000 students, 13 colleges. It has a nice campus. We are inviting you to visit it in Sharjah. And we have like a spread of colleges from arts and sciences till medicine, medical sciences, pharmacy, and other kind of medical or health sciences, plus the engineering and sciences. So it's a nice campus to visit. We, as Dr. Manar mentioned, that this is a part of our research group to work on different directions. And today we'll talk about the blind digital signatures. I'm sure that طبعا this presentation is more academic, so I wish that it will not be boring for you. It will not be also complicated for you. It will be, because we are academic, so we have to do it in an academic way, not in like in a conference like commercial one. So please be patient with us anyways. So the digital signatures, before we go further, the digital signatures, I'm sure all the people working in security, they know what is the digital signatures, what the importance of digital signatures. It's to provide authenticity, integrity, and other kind of security terms needed, especially for website accesses, for private messages to be exchanged, and so on and so forth. So the digital signatures, no two people in security, they have doubts the importance of those. And using the internet, which is open media for intruders, hackers, then the digital signature could be one of them. Doesn't mean that it is the best and secure way. It's still, still there are holes here and there, and these holes here and there. We have to work on them, and that's the work of researchers in the universities, to look at the holes and or vulnerabilities in this kind of solutions and try to find, the best or better solution. Not the best, because still the best is somewhere that's very hard to achieve. But that's the the idea. So if you look at this digital signatures in general, if you have a message to send, then what you do, you would stamp it with a private key and send it to across the air or across the internet channels, and then the receiver will receive that message, and then he will open it by his own public key, which is everybody knows. And then in this case, we are sure that this message has been stamped or originated from the originator. That's simple, like this, no more, no less. So that is the idea: to stamp with a private key and the or verify by the public key. Now, how you choose the public key, the private key, that's maybe the one issue that we have to talk about. And then we talk about the blinding, the signing. It should be blind, not blind, etc., etc. That's why what's our talk about it. So it's really one of very important issues in the electronic messaging. And if you look at the electronic signature, it has a little bit different from the regular signature, that our signature or handwriting signature. The handwriting signature, it's not changed. I mean, whatever the paper that you want to sign, your handwriting signature doesn't change. So it is always the same, no matter what is the kind of message you want to pass or to receive, and so on and so forth. But for electronic signature, a little bit different. The electronic signature is based, or is depends on the content of the message. That means it has different signatures for different messages, because the signature is based on the message plus the key. So these are the two things that we have to look at when we are signing a document. So the one difference, I'm sure a lot of you, they know this background. So it depends on the message. Then we have a different kind of signature, and there are few things that we have to take care. When you are designing the digital signature, the simplicity, easy to stamp, easy to verify. When you say easy to stamp, easy to encode. When easy to verify, they can decode. So these are the two parameters that the designer, the code designer or the digital signature designer take into consideration when he design the kind of so the recognition and verification of signatures has to be easy. Otherwise, we need high computation in the generation of the keys and high computation required for verification. So this will not be practical, especially when you are accessing an internet or you are accessing some private information on the website or somewhere else, because this is is needed for make it practical. And the digital signature, as it's mentioned here, they said to me that it will not be clear anyways. So that will serve the purpose of the authentication, integrity, and no repudiation. That's what the digital signature will be. So if you look at this picture, it's like summarize the idea. So we have Elise and Bob, and Elise wants to send a message to Bob. She has a message. She has a public, private key. You have a message, and the public, you are encoded or signing it. Then you send the message and the signature. On the other side, you take the signature and the message, you redo it again to verify it, and then you got M has to be the same as M and the signature, the one that you verify. It is used to verify that the message you receive is exactly the same message that after decoding. So this is the simple approach for digital signature. So it provide authentication, that you may make sure that this message has been stamped by the originator, and also provide the integrity. If the message has been changed somewhere in the middle, then that we receive the signature is not the same message. So that's why it provide authentication and reputation and integrity. But if you want reputation, you make sure the owner, then you need a trusted party. So in order to having another structure to include a trusted party in the middle, so you send it to a bank or you send it to a certified authority that will do the signing again. So he will decode it and then encode it again with a private or trusted party key, and then decode the other side. So these are if you need another signer or to help in verifying the originator. So the other one, which is the privacy. If we talk about the privacy, the message will be, according to the previous structures, the message will be sent as decoded, plain text. And if you want to do encoding them, then there are privacy. In this case, you have to include the encryption algorithms. This lecture is not for encryption anyways, but you can encrypt it by another key. That's what the picture is showing. You can use symmetric and symmetric key encryption. That's up to you how to do it. But anyways, you can encrypt it as another layer for privacy. If you like to have your message will be encrypted during sending and not in plain text as usual. Unfortunately, that this kind of digital stamping, digital verifying, it's based on not complicated mathematics, but it's a bit of mathematics not taught in the high school or basic bachelor degree. These kind of sciences that we use in encryption or stamping is called finite field. And the finite field, if you look at this picture, it shows that we have several kind of terminologies. I am not here to explain every one of these terminologies, but it gives you the idea that if you need to encrypt or decode or signing, then you need to know something about finite field. And the finite field, by the simplest in nature, it is a set of elements, and the operation of these elements will be resulting in members in the same family. That means, for example, if we are working in decimal from 0 to 9, then all the operation has to be from 0 to 9. So these are the elements that we are working with. And the finite field is a field that will be used for signing and verifying, and you look as we go where we can use the finite field. But the finite field, from its name, it's a field of numbers, and those field has parameters and has operations, and these operations are linked to the parameters. That's simple like that. But there are many kind of divisions in this finite field, started from a group to the field. Everyone has his own features. I will not go through the details, but it has its own properties for the finite field. One of the pioneer person in the finance is called Galois, and the Galois is a French scientist who started this finite field for other applications, but later the encryptors or the cipher people, they use it for the encryption and decryption, signing, all of these kind of operations that we will see as we go in the program or in the lecture. So what is the formal definition? The definition of a group? It is a set. Every member of member of the set like A, it's belong to some sort of field numbers or a set of values. So any X or Y belong to the group. And then their combination, the multiplication, the addition, subtraction, I don't know, all these kind of mathematical operation has to result a number in this finite field. Just an example, suppose we have a binary. When you add 0 plus 1, the result will be 1. 1 plus 1 will be 0. 0 plus 1 or 1 plus 0 or 0 plus 0, all of them will be included in the binary field. So it has to be in the binary field as well. But our binary is limited, so we have to extend it for another another set, and that set will contain another number that will be used, to do complicated kind of encryption algorithms that as we go, we will see some of them. But that's what the idea. We have finite field, and the finite field, the operations plus the elements, all together, they have to stay in the field, in the same field. And that group has to have the following properties, the mathematical properties. If you have a mathematical background, you'll see that's so simple. We have associativity, identity, and inverse. All these kind of operations that will be done by regular math or by regular basic mathematics, then can be done also in the mathematics of the finite field. By the way, the algebra that has been used in a normal numbering system, it will be a little bit different from the algebra that will be used for finite fields. That's just to give you an idea. That's not to be the same because it requires that the result to be stay in the field, and that's why we have different kind of algebra. It's called abstract algebra that will be used, to do the operation within the same finite field. Let me skip that slide here. So this is what very interesting group that is used in the encryption or in the also signing, which is a group of numbers. All the numbers that has greatest common divisor should be 1 between x and n. So if this is a property satisfied for all the numbers x, then we form a group from this. And that group has been, several kind of good properties used for encoding and for signing. So, by the way, the invention of these kind of groups, etc., is coming from the math people, not coming from engineering, not from computer science people, mostly from the mathematical backgrounds. And then we use it as engineers or scientists, computer scientists, to do these kind of algorithms. So we thank our friends in the math departments or math colleges to give us this kind of mathematics that we can use for encryption. So one of the famous kind of coding that everybody from in security working there know, it's called RSA, which is Rivest, Shamir, and Aldi Adelman. In 1977, they discovered RSA. And the RSA, which is a private and public key, so they derive 2 large number from their own multiplication. They use it, a fraction of this for the private, the other fraction would be for public. And then they use it for signing the private key and public key. Also, there is Al-Jamal, which is in 1984, is extension. RSA has been broken anyways, so we will have to go for another kind of encryption complexity like Al-Jamal 1984. It uses different way. The first RSA uses the fractional approach. The other one uses discrete logarithmic problem, which is a little bit complicated problem. And if you look down in the slide, you will see what is this problem here to find. We have h equals g to x, and then what's our job? We're giving x, we can find, we have to find x from h and g. So this is a complicated problem. So many probabilities that we can use in order to get x from h and g, and that's will complicate it the way anyways. So really more complication mean more difficulty in breaking the code themselves. I will skip that as well because it's just continuation to the discrete logarithmic problem where we have a complicated problem to solve if we are trying to decode or to break the code. Again, this is I will skip that one for simplicity. But one thing that I want to mention here in that slide is about DFH or the Diffie-Hellman key exchange, which is used, a lot for key exchange in the websites. So it's used again for using private public key, and then you're using symmetric key later. So it's some sort of kind of security protocol. So today's lecture is basically on the security protocol, how the keys are exchanged, how the messages are exchanged, who is knowing what, and so on and so forth. This is what we have to make sure that the exchanging of the information has more privacy, and hard to break, and hard to know, where to break and how to break. That's the whole idea of inventing several kind of algorithms in the security protocols. These kind of statements that is written in that slide, which one is harder, which is one easier, it's just maybe now, maybe later when quantum computing coming, then maybe all of these kind of coders or decoders can be broken. But For now, they say discrete logarithmic is harder than a fractional, but for sure this talk is not always valid, and you have to make sure what kind of computers that you are using for decrypting those. So that's just the general, very general from researchers' point of view. But for sure from the commercial part, they have another kind of difficulty when you are trying to breaking the digital signatures. And the digital signatures, there are various types of digital signatures in the market, and some of them are listed here, like RSA, very famous, Al-Jamal, we have Schnorr, and we have also DSS and elliptic or ECC, elliptic curve encoders or digital signatures. So many of those. We will go through them just quickly because we want at the end for a blind. Now we have till now it's not a blind. Everybody is knowing what we do. We are not doing the signer. The signer and the message owner are the same. So that's why it's not blind. Everybody, the signer knows what to sign, and the owner knows its own message and also knows the signer. So that's the idea. In RSA, it is using the fractional approach, as I mentioned. And in this case, we have the encryptor is simple, or the digital signer is simple. We have the message, and then we encrypt the message by message, finding the signature of the message by taking the message of some private key with this equation that's mentioned in the top. Take M to the exponent. Remember, all these kind of operations done in the finite fields, not done in the floating field that we are familiar with. So we are taking the message as a message in bits, and then you are exponent, making to exponent mod n. So where all our operations are in the mod n field, not in the regular kind of arithmetics. Then we send the S and M, the signature and the message. On the other side, you take the message, you revert the operation by taking the messages, the signature to the power of the public key. Then you have to find the same message. If you are not finding the same message, now we have a problem. The message has been broken somewhere in the middle. There is another way that you are using, a little bit message digest. In this case, you are hashing the message rather than taking the original message. So hashing the message itself, then the hash of the message you encrypt it or sign it and send it. On the other side, you take the message, the hashed part of the message, and then you compare the signatures between the original message and that. To just make sure that we are reducing the mathematical operation to be done at the transmitter. That's the main idea, to take a hash. Adatan hash is shorter compared to the bigger message. If you have one file of 1 mega size or 2 mega size, you make it short into 256 or 512 bits. So we have less computation time required, to do hash, and then we are doing the signing algorithm. This RSA. The key generation for RSA based on the fractional, so you have to N, Q, and P, and then you have to find the private. And so we have only two parameters. We have the private key and the N, and then the other side, the public key and the N. That's the all parameter that has been known at both sides. But in Al-Jamal there, he's doing more complicated. He is that in the transmitter, you have to have E1 and E2 and the public key, and there are many other parameters to be included in the signing and also designing. So if you look at Al-Jamal, it has two functions to be used, and the second function uses the result of the first function as well. So we have a complicating the way of finding the signature and the complicated way for encoding the signature itself. And then when you send it, you look at the signature, you are on the air, it's hard to reverse all these kind of operations to make sure. And the problem that we face in digital signature, that anybody can sign a message which is not himself, which is not his own message. Or he sent a wrong message with his own signature and let the user, the customer, believe that this is the message from another user. So that's the like forging the the actual username. So this is the idea. And in Al-Jamal, he's trying to make it complicated by using two functionalities, more than one private and public key, as is mentioned in that slide. So again, all this operation has to be in finite field, as I mentioned, which is another name called Galois field. So it's just a terminology used. And this is a variant from Al-Jamal. It's called Schnorr. And the Schnorr now it's like heavily used in many applications. You know, trying to replace Al-Jamal in many other applications because he introduced a new other complexity. If you look at the figure well, you see there is the hashing as well, hashing of the F1, and that will be a little bit complicated compared to the Al-Jamal. But Al-Jamal by itself is complicated. Now he's doing more complication to make it harder for the breaker to sign a message which is not his own message or not originated by the message. So this is a Schnorr. So we RSA and Jamal, then the Schnorr. This is the third one. And the DSS, which is the standardized digital signature standard. It is designed by NIST and NSA in 19. There are some revised approaches in 2000, the latest one. And also use SHA as a hashing algorithm, SHA 256. And then there are several other standardization that has been used in this. So this is for the DSS. And if you compare DSS with the KSA or RSA, it's sure that it's more keys, but in the same time the computation is faster. Because as I mentioned, the property has to be fast for encryption and decryption. Both of them for signing and designing. That's what I mean. To be faster. And also, if you compare to the Jamal, it's smaller in size because if you want to do it on embedded devices or on IoT devices where you need light signatures, then you have to make sure about the size of the memory, computation time required, and all these kind of small, tiny things that is required on the hardware. That when you encrypt or decrypt should not be taking that much time. That's the idea. So it's best on RSA and best on Al-Jamal in something. Some places there's nothing here mentioned about the breaking time and so on and so forth, but they are very similar in that kind of structure. And the Schnorr and the elliptic one is now also emerging, the kind of the signature. You're using elliptic curves. And again, the kind of the signatures here, they are sending two signatures rather than one signature. And if you look at those two kind of signatures, how they are produced, again, by using two functions, all of them, they are working in the finite fields, and they are stamped by the public keys. And in the receiver, we need just one private key to do it. So I will leave the complicated of generation and reduction, because it's well in standard. Everybody knows in the elliptic digitals how it looks like, especially people working in the encryptor area. Why ECC? Why elliptic curve cryptography? Because it is shorter, less computation, low power requirement, which is for IoT devices and for embedded ones. And web server that really they have very fast in responding, especially for if you are requiring, to sign so quickly, and you have a servers that have to serve several clients at the same time. So you need fast and quick answers. So it is, one of the good alternatives for HTTPS kind of secure layer. So if you look at also the key size compared to the other kind of, it's shorter. It's shorter compared to the, for example, the RSA and the Diffie-Hellman coding. If you look at the Rust on the right, it's only 112 in case of using the key is 56, while 512 in the case of RSA. And if you go further and further, it's still one of the best, really one of the best kind of signing algorithm or encrypting algorithm which is used in the field. Again, as I said, all these kind of algorithm based on the group operations, which is a finite operation, so I will not go through that. It's heavily math. I don't know, we're teaching in the master or PhD level, the kind of this mathematics used in the cryptography. So I leave that few slides, for, otherwise this like will be a lecture in the university, not in a conference. So I leave that slide, and I will leave that slide as well, discrete log problem. But anyways, these slides will be shared to you on the website, so you can go on to the details in your free time if you are interested in such kind of operations. So I will leave these because these are all versions of elliptic type of cryptography. So I leave that because it's just another variance of elliptics. Small addition here, small addition there, to close one hole and to close two holes and so on. So I will not go through all of them because they are just tackling few problems happening in the ECC during implementation. So we'll leave that. For that. But now if you look at the summary, what we are talking about, we are talking about digital signature, and depends on the message and some information unique to the signer. And Al-Jamar or Schnorr or DSA or DSS, all of them based on exponentiation. That means M to D or M to E, etc. Call exponentials. And there are other which depends on log algorithms, not exponential. So we have both, but on log and exponential they are related to each other anyways. So it is just like two faces for the same coin. And the variation, some textual signature they include time. And in this case, when you include timing into that, then the signal or the signature will be a little bit more make sense because it will be changed from time to time. But let us come back to all these are introductory things to come to the mainstream of today's point or focus, which is on the blind signatures. It look like it's a signature, normal digital signing, but it's blind. What is blind means is the following. Really, this kind of it's not that new. It was developed and introduced by Dr. David Chaum or Chaum. Both names could be accepted here, depends on where are you. And it's a problem that signing the document that you cannot read. That means the signer and the originator, they don't know each other. You have a message, but you want your message. When it's signed, it's not known to the signer. For example, if you want to send the money, and you want the electronic money, and then you want to say that the signer will be a bank, the bank doesn't know how much money in that token. So that's the idea. So the originator of the message and the stamper or the signer, they don't know each other. That's the purpose of the origin of the blinding signatures. David Chaum, this is some his very simple background about this guy. He's American. He's working in a cryptographer. He's one of the inventors of the eCash or e-money that is used in Bitcoin and other kind of electronic money. And also he is invented many cryptographic protocols, and he was founded what's called DigiCash and Electronic Money Corporation. This is one of the pioneer work in the electronic money. In his paper in 1981, which is about 27 years ago, he said, or even more, then he said that any traceable electronic mail, retain addresses, and digital pseudonyms. So he is trying that whenever you send a token or message, nobody can know who is the originator. He cannot trace you. He cannot link two messages coming from the same originator. That's the idea, the basic idea of his kind of approach to generate this kind of idea of the blind signature idea. So blind signatures are typically employed in a privacy-related protocols where the signer and the message, signer and the message are different parties, as I mentioned there, especially the money. The money is a bigger trouble. That's why the money owner and the bank, they have to, maybe sometimes I am not trusting the bank or vice versa, or not trusting the internet in general, not the bank, because the bank is already protected by the governmental bylaws or laws. But when you are talking about the money in the net, then you have to be careful who trusting who and how we can trust. I will not go about this guy. I will leave this, to read it by yourself about David Chaum, about his background, how he started to think about electronic money, electronic cash, DigiCash. So I leave that, for your information. It's a good information that you can read whenever you have a free time. And the two things that we have to be careful, and even this guy is starting to think about, is called untraceability and unlinkability. So these two acronyms that is used with the blind digital signature. Something that you cannot trace, That means you don't know, for example, if you buy some goods, then the buyer, from where you buy, he cannot track you as a buyer. He know that you are a buyer, but who are you, from where are you coming, etc. He should not trace you. When you pay, he should not trust you. Should not trace you, not trust you. And unlinkability, that's will good, give the payee or the one that from where you buy or from where you are getting the money, he should not link two transactions coming from the same originator. So that means he could not link the messages together. That's the two ideas. Something that's not traceable, something that's not linkable. So he proposes an electronic coin to be a number. Okay. But I'm seeing that time here. It's okay. So to be a number with a signature and blindly, signed by the bank. I will come to this example anyways at the last, but I just want to give you the same example that is by voting. Voting and e-cash, really, these are the two critical things, not only in all the countries. You want to say voting for one person, this vote should not go to another one. Because if it's go to another one, there's a big problem. And the organization or the election, they know that you have a yes. But who is you? He doesn't care. But at least he knows you are an elector. You have one that you are allowed to elect. That's what I'm trying to say. So he proposes, let us go to the second slide, it's better. Or let us take this one before we go to the slide, which is anonymity. The first thing is about the terminology called anonymity. And anonymity, sometimes we might call it linkability, which prevent the signer from linking later the blinded message to any blinded version that it may call upon verify. What it doesn't mean? That means when I send message, I should blind it. When I blinded the message, send it to the signer will stamp it. So when you blind it, means he doesn't know what's going on inside. He see an encrypted message. Now, blinding is not blinding means make it black. Blinding means you are making the signal chaotic, by a random number. You just multiply every bit by a random number, dynamic random number, and when you see it's not related to the original ones anyways. So you see a blinded message, here sign it. Maybe you can ask, how can the bank stamp something that he doesn't know? But that's the agreement, that's the agreement. He will not see what is the content. But once he signed unseen things, coming back to the original, and the original has to make sure that the bank sign it, not anybody else sign it. That's also, we'll see in the slide about the block diagram. And we need to verify this, to verify that the bank certify this kind of signing by the originator and by the payee, the one that you pay to. So these two have to make sure that these are verifiable. So these are the two terminologies that you please remember. And this principle that in order to guarantee that we have the signer and the message author or owner, there should be different parties, not the same party as the normal digital signature. Normal digital signature, you are the owner and you are signing it. Now you are the owner, but somebody else will sign it to you, not you, like your manager, your vice chancellor, not you, but you have the origin of the message. Just to make sure that this message is somehow it's authorized by the bank or by somebody else. And the blind signature, the one that we want to continue on that, is to be used in an application where the privacy is an issue. The privacy is an important issue to look at that. And the blind signature protocols has two properties, as I mentioned, blindness and untraceability. Now we'll leave anything related to the math. I try to avoid it. And now let us look at another terminology that we want to share with you is about anonymous. Anonymous, something that you, without name. When you go and during the website, you want to be a guest, or you want to be anyone. You don't want to release your personality. You release your credentials to the website. This is called anyone. So that's what the word that we have to use when you are sending a message. The bank doesn't know exactly what is inside. He just says, receive a message from an authorized place, and he will sign it. That's called anonymity. So the anonymity is two terms, which is the pseudo-anonymity, the word that is used in computer science, and also unlinkability, so that we cannot link two blinded messages to the same owner. That's the idea. And the payer anonymity again is very important. When you are paying the money, the one that you pay to, it has also no information about your credentials. Who are you? Where you are living, etc. Because otherwise, you are releasing some private information of yourself to the buyer, to the one from your buying things, yeah, which is not always good, you know, for the buyers. They want to buy things, but they don't want anybody to know who am I or why I am doing this. Okay, so let us look at how the system look like, you know, the blind signature. Look at this block diagram. We have we have the user, the one that originator of the message, and we have the signer. Again, there are two different parties. The user has the message. The first step to do is blinding it by a random number. Then you send the blinded message to the signer. The signer, the poor guy, take the message, stamp it with his private key, send it back to the owner. The owner now, he has a signer signing on something blind. So he has to verify, he has to be unblinding it. He unblinding it and then send it, you know, when he goes to the buyer or to where to buy, then he send it unblind because, you know, you can say what I want to buy. So the blinding process is done at the user, and the verifier, or often the signer, doesn't know, you know, what he signs. And really the signing or blinding, it is just like regular, if you look at this mathematical approach, it is just simple randomizing the message. Randomizing, meaning you multiply the signal or the message by a random number. So when you multiply, you have a random numbers, and those random numbers, you cannot revert the operation. And if you look at this diagram, it's just a mathematical diagram about previous figure. So you send the message, blinding it with R, then you send a blinding M and R, and the bank will take it, sign it with his own key, then going back, he unblinding, and then he will verify it by having the original M in himself, because he has the original M. But in some other places, they want to make it not harder, but at least partial blinded. So he will not blind all the message, he will blind part of the message. So he leave part of the message plain text as is, especially the time, or some other information that we agreed upon, and the other one is blinding, which contains sensitive information. So he sent it. Again, this structure is also existed in the market, where you blind part of the message, not all the message. That's another alternative to the blinding process. But the procedure is the same. But you have to agree with the signer that I'm sending part of the blinded and the other one not unblinded. So he will do it, you know, without looking at these kind of details. But this is a good way of blinding some and not blinding the others. These are the diagram. You can look at it later, which is a compromise of the mathematical or systematic way of doing the kind of signing, partially signing. This is more detail about the actual algorithm, where you choose P and Q for a very large P number from N. So in N equals P times Q. So you choose P and Q randomly, but the multiplication has to be equals N. And the N is the finite field that we are using for mathematics. You know, look at this problem here. And then the bank will publish all public keys for himself. And then you are using your own private key to send, and he will stamp it with his own private key, and then you design it by the bank public key, which was already. So this is a process about taking debiting money, and then also the withdrawing money again. So about the debiting, which is drawing money, and then how to pay. So these are some details. I will leave that for because the details about the mathematics, how to do them. All of them are by exponentials anyways. You are just taking the message, exponential, and so on and so forth. I will go directly to the examples because this is another, by the way, when you implement the blind signature, we are using the standard ways, either RSA digital signatures way or using Schnorr or using Al-Jamal or all these kind will be reused, but with blinding. That's the whole idea. And there are some starting research in our group is to use those in blockchain. So because the blockchain using anyways hashing and signing, digital signing of the transactions. So we are trying to use those kind would give you more privacy of the information to increase the security of the transaction that are linked in the blockchain. So just starting a project on this. So this is how the Schnorr algorithm will be look like. This algorithmic, so if you want to program it, it will be quite easy. You are randomizing, then you get the value and hashing it, and then you add it to a random value, send it, and so on and so forth. I will leave these details here because of the time issues. But let us go directly to the last two slides. Sorry, I want to really to explain this because this is very important. Where you because now the critical thing that you are not releasing your credentials, you are not releasing yourself to anybody. And in this case, who can? If you do some mistakes, who can catch you? So you need to present you as you to some judge, some place where they certify that they know your identity. Whenever there is a problem in the bank, in the buyer, seller, whoever in this process, if they have a problem and they cannot find you, because they cannot trace you, the only thing is to go to the judge, and the judge has all these credentials to find you. So this is what's called, a fair model. The fair blind, where there is a third trusted party that will catch you somewhere, to find you whenever there is a problem, because nobody knows your identity, nobody can trace you, nobody knows your all these details. Then we have a third party that take this kind of responsibility. The blind signature, it's used in many applications, really many applications. One of them is identity management that explained in that slide. We'll leave the slides with the conference organizers. But there are other two things that I want to share with you in the application in voting and the application in the e-money. This is the voting. Look at the picture here. We have the voter down here. The voter, and the voter itself, then he want to vote, blindly say, oh, yeah, I want this or that, or yes or no, or something like that. So he has his own message, and he doesn't want this message to be shared to anybody, even the election authority. So he send it blindly and authenticated and blinded to the election authority. The election authority's job to just certify that you are eligible to vote. That's only what's there, but he will not see what you are voting, what kind of message that you use. And then he will return this signature for the blinded message back to the voter. And this voter, he will send his token or his cast vote to the voting center. So the voting center, they have the access that to the election, because there are some relation between them, and they assured that this guy, when he sent the vote, it's real, it's something that he is eligible to vote. That's the basic thing. But nobody knows except the voting center. Not anybody. Election authority, just to make sure that you are certified, you can vote. So this is an explanation anyways. About the money example is also shown here, that if you want to withdraw money from the bank, because now e-money or e-coins, then also you send the amount blinded. So the blinded message will be sent to the bank, and the bank will be signing that blind message back to the owner of the money, which is me. And then whenever you go to any merchant or any mall, and then you want to use those coins again regular, because they are and even here the identity of you is not declared to the merchant, which is in that. But if you want to double check that you are the owner of the money, he will not ask you, he will ask the bank. And again, the bank He just have it, the public and private key. So these are the, the message for the e-money. I will stop at this point because the rest is just an explanation of that slide. There are more slides to come, but I think I don't have much time. And I wish that it was not a boring session, because it's talking about like you are in, back to the university and talking about finite fields and so on and so forth. So if you have questions, I will be happy to answer. If it is required time, we can also make it offline.
Well, I think the crowd is very satisfied with your talk. So thank you, Dr. Qassim and Dr. Manar, for this impactful closing keynote. And thank you for gracefully wrapping up our conference today.